Okay guys, so today we're going to talk about section 2.6 in our book, which is a topic called related rates. And this is a really big, really important topic we're going to do in AP Calculus this year. So if you recall in the last section, we talked a lot about the chain rule and how the chain rule helps us find dy dx implicitly. So we just did implicit differentiation. That'll be on the test next week, just looking at taking the derivative of y with respect to x. So another important use of the chain rule is to find rates of change of two or more variables with respect to time. Let me show you what I mean. These are called related rates problems. Suppose we have water draining out of a tank that's shaped like a cone. The volume, V, the radius, R, and the height, H, are all water level functions, or the height, H, of water level are all functions of time. So since we're talking about volume for a cone, we could relate these three variables together using the formula for volume, 1/3 pi r squared h. What we want to think about here is differentiating this expression, differentiating each variable with respect to time. And think about what's going on here. If this is representing volume of a cone and water is draining out of the cone, as time passes, what happens to the volume? Goes down. So the volume is going to decrease. Likewise, the radius of that circle will decrease, and the height of the water will decrease as time goes on. All right, so we're going to take the derivative. Remember our formula, V equals 1/3 pi r squared h. So we want to take the derivative with respect to t. Well, the derivative of V with respect to t would just be dv dt. Now to take the derivative of this right side, it's a little bit more involved because r and h are both variables. Make sure you see what's going on. So the left side turns to dv dt. The right side, 1/3 pi, I left on the outside because it's a constant. Now to take the derivative of r squared h, we have to use a product rule. The derivative of r squared will be 2r dr dt, taking it with respect to t, times the second recopied, which was h, plus the derivative of h with respect to t, which is dh dt, times the first recopied, which is r squared. So this is all a product rule of r squared h with respect to time. So what we've done here is we've differentiated each variable with respect to t. And this is what we're going to use whenever we do these related rates problems. So let's look at an example here that just involves a generic function. Suppose x and y are both differentiable functions of t and are related by the equation y equals x squared plus 3. The question says find dy dt when x equals 1, given that we know dx dt is 2 at that moment when x is 1. We're going to take the derivative of this expression, both sides, with respect to t. So the left side, the derivative of y, is just dy dt. The right side, okay, the derivative of x squared, think about when we did implicit differentiation, it's going to be 2x dx dt, because we're taking the derivative with respect to t, not x. And then, of course, the derivative of 3 is just 0 because it's a constant. So now look at what we're trying to find out. They asked us to find dy dt. X is 1, and dx dt is 2. We're just going to put those numbers in, and dy dt is 4 at this moment in time when x is 1. That's kind of your most basic related rates problem. You'll see a couple of these in the assignment next week. All right, let's look at a more practical example. So consider a spherical bubble, and we know that air is being blown into it at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius of that sphere at the moment when the radius is 2 feet. Think about if you had a balloon or you're blowing bubble with a bubble gum or whatever, and you're blowing air into it, so it's getting bigger, it's changing as time passes. So what do we know here? We know that dv dt is 4.5. How did I figure that out? Well, we were told that the air was being blown into it at a rate of 4.5 cubic feet per minute. Well, cubic feet is a measurement of volume. So the per minute tells me that that's the rate of change of volume, or dV dt. And we know that R is 2. That's the moment we're interested in. So that's the given information. Now think about what formula would relate all of this together. We're talking about the volume of a sphere. In case you've forgotten, the volume of a sphere is equal to 4/3 pi r cubed. Some of these geometry formulas you're going to need to go back and memorize again, but a lot of times in the problems, they'll give them to you. So for now, here's the formula for the volume of a sphere. And we're looking for the rate of change of the radius. So that would be dr dt. We're going to take the derivative of this expression with respect to t. The left side's the easy part, that's dv dt. 4/3 pi is a constant. The derivative of r cubed is 3r squared dr dt, because it's implicit differentiation with respect to time. So simplify a little bit, you see the 3's divide out, and then put in what we know. We know dv dt was 4.5, and we know r was 2. So if we go back and solve for dr dt, we get approximately 0.09. Use the correct unit. Since it was cubic feet, the radius would be feet per minute. The dr dt is 0.09 feet per minute. And I didn't show it all in the PowerPoint, but all I did was I took that equation that we had for dv dt and I put in what I knew and solved for dr dt. So that's kind of the gist of how most of these problems are going to go. So some steps for solving related rate problems. If it's helpful, draw a picture. Didn't do it in the last example, but in the next one you'll see it's going to be helpful. Write down what you know, what they tell you. Did they tell you dv dt? Did they tell you dr dt? Did they give you a time? What did they give you? Write down what you're looking for. What am I looking for? In the last example, we were looking for dr dt. Come up with an equation that puts it together. Volume of a sphere, volume of a cone, Pythagorean theorem, whatever it is that you're working with. Differentiate both sides. Everything that's a variable gets differentiated with respect to t. Then, of course, put your numbers in and evaluate it. One more example. A balloon is rising from ground level. The angle of elevation is increasing at a rate of 0.04 radians per minute. How fast is the balloon rising when the angle of elevation is pi/4? They gave us a picture here to use. We know theta is pi/4. The radians per minute, think about what quantity that would refer to in this picture. It's a rate. So that's d theta dt. Angles are always going to be measured in radians. So anytime you see radians, you know it's referring to an angle. Radians per minute would be your d theta dt, your rate. What do we want to know? They said how fast is the balloon rising? So the height represents the balloon, how fast, or the height represents where the balloon is. And they said how fast is that changing? So if h is the height, they're looking for dh dt. How fast is the balloon rising? So an equation that puts all this together, think back to trig. If I'm looking at theta, and I'm working with opposite over adjacent, they told me this was 500 in the picture. So the equation that relates those is tangent. Tan theta is opposite over adjacent, or h/500. Now, to take the derivative, make sure you see what I did here. The left side, tan theta, is a chain rule. So the derivative of tangent is secant squared, evaluated at the inner, which is theta, but times the derivative of theta, which is d theta dt. This is a chain rule here. And then think about h over 500, that's the same as 1 over 500 times h. The derivative of that would just be 1 over 500 dh dt. Really think about this. Make sure you see this chain rule of this left side. You have to think of tangent as your outer function, theta as your inner function. Derivative of the outer evaluated at the inner, which is theta, times the derivative of theta, d theta dt. Then let's just put in our quantities. So we knew theta was pi over 4, so I put that in for the angle. I knew d theta dt was 0.14. dht is what we're solving for. So if we calculate those numbers, simplify, get dht is 140 feet per minute, and use the same units. They used 500 feet in the picture, and it was a rate, minutes for the time, so we're going to use feet per minute as the change in the height.